And now we are on 3.3, molarity. So in this section, we're going to describe the fundamental properties of solutions, calculate solution concentrations using molarity, and perform dilution calculations using the dilution equation. So we've talked about pure substances composition in the past two sections, but mixtures also are encountered, and probably encountered a lot more frequently than pure substances. But we can also figure out relative compositions in mixtures to help determine properties as well. So just to kind of give you an example of a mixture you may see for my fellow caffeine addicts, sugar or sweeteners added to coffee to make it a pretty complex mixture. And the amount of sweetener you add really determines the sweetness of your drink. For instance, I like my coffee pretty sweet. I actually don't even drink coffee that often. I'm a tea drinker. I like my tea especially pretty sweet, or either sweet or not sweet at all. There's no in between. So solutions occur very frequently in nature. These are another term for homogeneous mixtures, if you recall from chapter 1. And they have uniform composition and properties throughout the entire solution itself. And we can find the relative amount of a given solution, which is called its concentration. So there's two components to a solution. The solvent, which is the component in it that has the higher concentration. It's much higher concentration than everything else. So that would be like water when you add, or the coffee itself when you add the sweetener to it. And the solute, and this is the lower concentration than the solvent. So this is what's dissolved in the solvent. If you have a solution where you have water as the solvent, this is called aqueous. And we saw aqueous last chapter when we had acids. You saw the abbreviation AQ. That means dissolved in water. So molarity is defined as the number of moles of solute in 1 liter of solution, exactly 1 liter. And when we say the concentration of something, we may say, oh, it's 5 molar. Okay, so molar is how we say it when we're speaking. And it's abbreviated with a capital M. You can also, instead of putting the big M for molar, some people prefer to just put, like moles over liters, because that's what it means, and sometimes it's just a little more helpful to figure out units. And molarity is very, very common in chemistry. You're going to see it all over the place. So it's really important to understand it and how to use it. So for instance, if we're told we have a soft drink with 0.133 moles of sucrose, we want the molar concentration of sucrose. We have 355 milliliters. So we need to first take that 355 milliliters, turn it to liters. They did everything in one step, but just in case, 355 milliliters. And there is 1 liter for every 1,000 milliliters. Okay, so that's 0.355 liters. And so we take our moles, divide it by our liters, and you get 0.375 molar, or 0.375 moles per liter. And then here's a little follow-up question. How much sugar, or in moles, is contained in a small sip, about 10 milliliters? So we have 10 milliliters. Let's first change this to liters, because our molarity is in terms of liters. So remember, there's 1 liter per 1,000 milliliters. And then we can use our molarity as a conversion factor. We could rewrite this. Well, actually, no, we're fine. So we could say we have 0.375 moles for every 1 liter. We could also say 1 liter per 0.375 moles, depending what we need. We want moles on top, because we need liters on bottom. Okay. Calculator go. Punch that into your calculator, and we get 0.004 moles of sugar. See, all our units cancel out, leaving us with moles. Okay, so here's another example. We're told distilled white vinegar is a solution of acetic acid and water, and we're given 0.500 liter vinegar solution that has 25.2 grams of acetic acid. We want to know the concentration of acetic acid in molarity. So remember, molarity is moles per liter, and we're given grams of acetic acid. So what do you think we should do? We need to go from mass to moles using molar mass. So they did it all in one step to get the moles of solute, which is moles of acetic acid. So recall from chapter 1, the solute does not have to be a solid. It can be a liquid. In this case, acetic acid technically is a liquid. Nonetheless, 25.2 grams of the acetic acid times 1 mole per its molar mass of 60.052 gives us moles of acetic acid. Okay. Divided by 0.500 liters of solution, we get a molarity of 0.839 molar, or 0.839 moles per liter. And there's just a label for what your vinegar might look like. All right, so now let's say we're making lemonade. And when you make lemonade, you add some lemon juice, right, and some sugar, and then you add water to it. So let's say you taste it, and the sweetness seems okay, but the lemon flavor is still a little too powerful, or maybe even both are a little too powerful. So what do? You add some more water, right? You're diluting the lemonade. But did the actual amount of lemonade change? No, because we're not adding extra lemon. Okay, so this is called dilution, and this is where the concentration of a solution is lessened by the addition of more solvent. So this is a way of making solutions of a desired concentration. Sometimes you make what's called a stock solution that has a high concentration. Okay, I believe you're going to do this in your Labster lab. And then you're going to take that and take small amounts to make smaller concentration solutions. So here's an example of a dilution. The cylinder on the left they both have copper nitrate in them. They have the same amount of copper nitrate, the same number of grams, but the one on the right is more dilute. You can see there's more solvent here, okay? But the actual mass of copper nitrate is the same. So if we wanted to calculate the molar amount of a solute in solution, that's equal to its molarity times the volume, right? Moles per liter times liters gives us moles. So that's let's say we're looking for our starting moles, and then we want to know how many moles we're ending with. It would be the same thing, just a new concentration and a new volume. But like we said, the number of moles doesn't change. So these guys are equal. So then that tells us we can set those two equations equal to each other, and we get M1 times L1 is equal to M2 L2. But it doesn't actually have to be only molarity for your concentration, and your volume doesn't only have to be in liters. As long as your units are the same on both sides of the equal sign, they cancel out. So we use just kind of neutral variables here. We say C1 V1 equals C2 V2. First concentration times your initial volume is equal to your second concentration times your second volume. So this is our dilution equation. As long as you know 3 of them, you can find the other variable that you need. So for instance, like I said, the 1s is what you're starting with. So this is usually your concentrated, your stock solution. And then the 2s is your dilute solution. So we're going to look at some examples where you're going to see this come into play and how to use it. So to start, here's one. We're told we have if 0.850 liters of a 5 molar solution of copper nitrate is diluted to a volume of 1.80 liters by the addition of water, what is the molarity of the diluted solution? So we're told a C1, and C1 is 0.850 molar. And we're told a V1, Oops, I'm sorry, that's V1, not C1. And that's liters, not molar. We're told C1 is 5.00 molar. And we're diluting it to a volume of V2 of 1.80 liters. Okay, so you can see here, we start with our dilution equation. We're solving for V2, so we need to divide both sides by C2, by V2, we're solving for C2. And we find that C2 is equal to C1V1 over V2. And then it's plug and chug. And you can see that down here, 5 molar times 0.850 liters over 1.80 liters. You can see our liters cancel out, and we get 2.36 molar. It makes sense because we have a higher volume, so we should have a lower concentration. So make sure to think about this to make sure that your answer makes sense to you. If you go up in volume, you go down in concentration. Okay, you go down in concentration, you go up in volume. Here's another example. What volume of 0.12 molar HBr, hydrobromic acid, can be prepared from 11 milliliters of 0.45 molar HBr? So let's start by figuring out what we know. Okay, so we are told this is our C2 equals 0.12 molar. And we're told we have a V1 of 11 milliliters and a C1 of 0.45 molar. You do not have to change your volume to liters here because our molarity is the same on both sides. They're going to cancel out and you would wind up with milliliters as your volume anyway. Your book changes it to liters, that's fine too. Just look on your homework and whatnot for what units it says. If it doesn't specify, it shouldn't matter. We have C1V1 equals C2V2. We're solving for V2, so we got to divide both sides by C2. So V2 equals C1V1 over C2. So that's 0.45 molar times 11 milliliters divided by 0.12 molar. We see those cancel out. And we get 41 milliliters. Or 0.041 liters. And that makes sense, right? We're adding to our solution, we're diluting it, so we should have a higher volume than what we started with. Okay, and here's one more example. What volume of 1.59 molar KOH is required to prepare 5 liters of 0.100 molar KOH. So potassium hydroxide is what we're looking at here, and notice we're going backwards. We want to know our V1. We're told our C1 is 1.59 molar, and we're told a V2 is 5 liters, and our C2 is 0.100 molar. So make sure you read these carefully. Okay, C1 V1 equals C2 V2. Divide both sides by C1 so we can get V1 by itself. V1 equals C2 V2 over C1. So V1 then is equal to 0.100 molar times 5.00 liters divided, whoops. Divided by 1.59 molar. We see molar cancels out, and we get that V1 is equal to 0.314. Okay, and this makes sense. It should be a smaller volume because that's what we're diluting. And that is how we use the dilution equation. And remember, you can use any type of concentration. So in the next chapter, we're going to talk about other solution concentrations. You can do any concentration, whether it's ppm, ppb, even percentages. As long as it's the same units on both sides of the equal sign, you can use any units for this equation.